Hello again and welcome back. We'll be going through questions 11 to 15 of the mock paper in this video. In case you happen to just chance upon this video without having seen the earlier videos, or perhaps even without having seen the questions in advance, the mock paper is linked in the description below. So do give it an attempt first before watching this if you haven't already done so. Alright, let's get straight into the questions now. For question 11, we have a circle, two parallel chords which are a distance 7 apart. And we are asked to find the area of the circle. Now by distance between the two chords, it means perpendicular distance, right? And that makes sense because the two chords are parallel to one another. So it is reasonable to talk about perpendicular distance. Now, I believe the easiest way to proceed would be to draw a line through the center that is also perpendicular, and that will have length 7. We want to make use of the fact that they are symmetric. In a circle, you have lots of equal things. So we can say that you would split the 20 into 10 and 10, and split the 22 into 11 and 11. Now, I would also like to make use of something that gives me the radius of the circle, since that is after all what we need to find in order to get the area. So I'm going to draw in the radii here and here, which gives me a couple of right-angled triangles, right? This length r. And now I'm going to call these A and B. I'm going to give myself a couple of equations so that I can find out what is A and B and consequently find out what is R. And the first equation is just A plus B equals to 7. That's pretty clear. The other equation comes from using Pythagoras' theorem on both of these triangles that I've just drawn in. So 10 squared plus A squared is equal to R squared, which is also equal to 11 squared plus B squared. Now, in particular, what this means is that my A and B are related to each other directly. I can kind of ignore the R squared for now and just rearrange the equation as A squared minus B squared is equal to 11 squared minus 10 squared, which is 21. Now, this is wonderful because we have a difference of squares factorization. So this is equal to 7 from our earlier equation, and so this would be equal to 3. And it is pretty clear that if A plus B is 7 and A minus B is 3, we can find A and B. A would be equal to 5 and B would be equal to 2. So therefore, substituting back into the equation, R squared would be 11 squared plus 2 squared, which is 125. And n is equals to r squared. So this would be the answer. So whenever you have a circle, one of the key things that you want to use is that, well, in a circle, all the radii are equal to each other. So when you see the center of the circle being marked out, you want to draw some radii from it to points on the circumference. And even if you don't see the center being marked out, it may still be a good idea to draw it in, because you kind of get a chance to relate many things to that same length of the radius. Okay, question 12. Let P be the product of all values of x such that this equation holds. I don't really want to read it out. Find the absolute value of P. Remember, absolute value of P isn't anything too complicated. It just means that if P is negative, then remove the negative sign and give me that value. So that is usually used when the answer is negative, but in order to indicate the answer for the SMO in the answer sheet, it needs to be positive. So this is the main reason why they say this at the end. Okay. Now if you look at this equation here, it is very obvious that we're not supposed to add them up by making a common denominator. It is going to be way too messy. However, you would realize there is a very noticeable factorizability of all these denominators. In fact, the first one is x plus 1, x plus 3. The second one is x plus 3, x plus 5. I feel like writing dot dot dot, but there's only 4, so I'm just going to write the other 2 down as well. This would be 5 and 7, and the other one 7 and 9, as you can see. So clearly, this is not a coincidence, right? Because 1, 3, 5, 7, 9, they're all odd numbers, is one thing, but the factors keep repeating throughout. So this is certainly not coincidental. Now, at this juncture, if you want to add this up, what you need to notice is that the difference is always 2. And when we have these numbers whose difference is always 2, we can split it up using partial fractions. Perhaps a number of you are more used to the numerical version of this. 1 over 1 times 2, plus 1 over 2 times 3, plus 1 over 3 times 4, and so on. This is in terms of x, but we can still do the same thing. So the first fraction becomes 1/2 of 1 over x plus 1 minus 1 over x plus 3. The next fraction becomes half of 1 over x plus 3 minus 1 over x plus 5, and likewise for the other 2. Great. So I can do a few things. One is, of course, to cancel out all the things that are repeated. So we have only got 2 simple fractions instead of 4 rather messy looking fractions. I shall also multiply 2 over. So we have 1 over x plus 1 minus 1 over x plus 9 equals to 1 over 1011. Now, these 2 fractions here, we can just subtract them so that we have a single fraction. Right? The top would be x plus 9 minus x plus 1. So we get 8 over x plus 1, x plus 9 equals to 1 over 1011. I will cross multiply. 8088 equals to x plus 1, x plus 9, which can be expanded, so let's just do it immediately. Move this over. X squared plus 10x minus 8079. And this would give you the product of solutions. You don't have to try to factorize 8079. If I'm being perfectly honest, I'm not even sure whether x is nice. Maybe it is. But the important thing is that since we want the product of all values of x, the product of solutions in a quadratic equation, you can just use this value at the back divided by the x squared coefficient, which is 1. So product would be negative 8079. And your answer, which is the absolute value of p, is 8079. Great. This is way less complicated than it may initially appear. On to question 13. So in the figure below, PA naught rather is 243. PA naught is perpendicular to A naught A1, and A naught P A1 is 30 degrees. So he proceeds to say that actually you continue writing these down using that exact same set of rules. Right? So A naught PA1, which we already know is 30, is the same as this angle being 30, it's the same as this angle, which should be 30, and so on. and PA1 is perpendicular to A1, A2, PA2 is perpendicular to A2, A3, and so on. So you have, again, a bunch of extra right angles. The question is, what's the largest positive integer n such that the length of PAN is an integer? So the lengths that we care about are all of these here. Right? PA1, PA2, PA3, and so on. We want to know how do these lengths look like. Well, that would normally be a difficult task, but we have this 30 degrees down here, which is really useful. Because with this 30 degrees down here, you get a bunch of 30, 60, 90 right-angled triangles. Now, please remember and be aware that for right-angled triangles with these angles, 30, 60, 90, they have a very special ratio, which is that this is 1 is to 2 is to square root 3. And the reason is that if this is 60 degrees, then this is half of an equilateral triangle. So if you were to draw it in here, the reflection, then it would be just 1 is to 2 because you have half the equilateral triangle. And square root 3 comes from Pythagoras theorem, right? 2 squared minus 1 squared is 3, so that is a square root of 3. Now this means that if this is 2, 4, 3, the ratio is square root 3 is to 2. So PA1 is going to be 2, 4, 3 times 2 over square root 3. But then PA2 to PA1 is in that same ratio, so it's going to be times 2 over square root 3 again. Which would be 243 times 4 over 3. This is going to be an integer since 243 is divisible by 3. Now, in fact, you realize that this is going to keep on continuing for the rest of our pattern, and 243 conveniently enough is a power of 5. It is 3 to the power of 5. Did I say power of 5? Sorry, I meant a fifth power of 3. And so this can continue, and every time you have the multiplication by 2 over root 3, it means that PAN is 243 times 2 over root 3 to the power of n. Now, obviously, your n has to be evens if you want it to be an integer. Because if n is odd, then you will still be left with a square root 3 inside, which cannot be an integer. Now, every time when you have two terms, you have an over 3 in there. So that means that with 3 to the power of 5, you can divide by 3 at most 5 times. And if you can divide by 3 at most 5 times, that means that your maximum n is going to be 10. Because dividing by 3 to the 5 would be the last time where you can divide by 3, and after that you cannot divide by 3 anymore. So after n equals to 10, either you would get square root 3 or you would get dividing by 3, neither of which are going to give you an integer. Question 14. Let x, y, z be positive real numbers such that 2x plus y equals to z squared and y plus z equals to 4x squared. Determine the value of 20xz minus 10y over z. Okay, first up, it is usually not enough to find what are x, y, and z, 3 variables, using just 2 equations. Almost all the time, it means that there will be multiple ways in which this can be solved. But even though there are multiple solutions, x, y, z, whatever the question asks you to find has to be fixed. So really what you need to do is to try to find out something interesting from just these 2 equations. And I think the most intuitive step for me to take would be to eliminate the y by subtracting. because that's the easiest one to eliminate out of all the variables. So you can eliminate y by subtraction, and you get 2x minus z equals to z squared minus 4x squared. Now notice for the umpteenth time that we have again got a difference of squares because z squared and 4x squared are both squares. So you have z minus 2x, z plus 2x. And I can move this over. And if you move this over, this is taking longer than I hoped. Alright. You move this over, you add z minus 2x, so you have plus 1. Now, notice that because they are positive, this one cannot be 0. So if this cannot be 0, then the alternative is that this must be equal to 0. And if this is equal to 0, it means z is equal to 2x. I can substitute it into here to conclude that y is equal to 4x squared minus 2x. So z is 2x, y is 4x squared minus 2x. And I will just substitute them all into here and see what I get. So it's 20x, 2x, minus 10, 4x squared minus 2x, over 2x. You get 40x squared minus 40x squared plus 20x. So 20x over 2x is equal to 10. Yeah, so at this point we still realize that we don't know what is x, and we don't really have a way of finding what is x, right? X could be any value as long as y and z follow these 4x squared minus 2x and 2x respectively. And that's often the case for many of these equations. You won't actually be able to find x, y, and z. Now, having said that, a little bit of a cheat would be to do something like guessing x equals to 1. If you had guessed that x equals to 1, you can trust that whatever answer you get is still going to be correct. So if, for instance, you just guessed x equals to 1, and then you realize that, oh, y equals to 2 and z equals to 2 also works, then that means that this must be the correct value once you put it in, because there can only be one answer to a SMO problem. So that's a way in which you can so-called abuse uniqueness if you can't solve a question. But obviously that isn't a complete solution. It's just that for the SMO, you sometimes can squeeze out a few extra points by making these guesses when you are quite stuck. Okay, last for this video will be question 15. The length and width of a rectangle are both positive integers. Given that the area of the rectangle is 3 to 1 larger than its perimeter, ignoring units, determine the smallest possible area of the rectangle. You can tell that this is describing something of an equation, so it only makes sense that one comes out with x and y as your length and width and writes down a concrete equation. So we can write down the area is 3 to 1 larger than its perimeter, which will be as such. Now, from here, I can rearrange it. I'll move over 2x and 2y. And what we do here is something that I like to call completing the factorization. Much like completing the square, the reason why we don't mind completing the factorization is that some extra constants appearing is fine with me. At the end of the day, all I want is x plus something times y plus something equals to some value, and then I can list out all the factors of that value, since it is mentioned that they are positive integers. Now, how we complete the factorization is pretty direct. I look at the first two terms and I try to factor out the common factor, which is x. And then I insist that I want to factor out y minus 2 from this back so that the whole thing shares the same factorization. Now, of course, this is not the actual factorization because one extra term, which is plus 4, has shown up. So just like completing the square, we need to return it back, minus 4. And now I'll shift this over while also factorizing this portion in full. So x minus 2, y minus 2 equals to 325. We are like the smallest possible area. The smallest possible area comes when the perimeter is the smallest as well. Essentially, you want your x plus y to be small. And if you want x plus y to be small, you should make sure that x and y are as close together as possible. So 325 is divisible by 25, and it is 25 times 13. So we can tell that it is unlikely we can do better than 25 times 13 in terms of making x and y close together. So that will be our choice. We can let this be 25 and 13. And so x equals to 27 and y equals to 15. So what's the area of the rectangle? 27 times 15 is equal to 405. Alright, and we'll stop here for this video. Do join us again for the remaining 2 more videos going through the last 10 problems. I think the last 10 problems are where most of the difficult questions are, so do look forward to that and see you again soon.